We'll proceed curl in calculus. Curl in calculus. How much we have come forward, that is as far as curl in calculus is concerned. Now we are pretty clear that a vector field is algebraic vector. Vector are of two types. One is normal numeric static vector, whereas there is another vector that is algebraic vector. Vector has component. First component, second component, third component, fourth component. If components are algebraic equation, if components are algebraic equation, then this vector is called algebraic vector, or this vector is called vector field. Okay, so if a vector has component that is algebraic equation, algebraic function, then this vector is called vector field, where this term curl come into the picture. If I have a vector field capital F, and then can I integrate this vector field along a particular line? Can I differentiate a algebraic equation along a particular line? That is called directional derivative along a vector. Can I integrate a vector field, not algebra? Can I integrate a vector field along a particular line, along a particular vector? That is called line integral, directional derivative and line integral. If I have algebraic function and I want derivative along a particular vector, that is directional derivative along a vector. If I have a algebraic vector, not function, algebraic vector or vector field, if I want to calculate integration along a particular line, then it is called line integral. If that line or the vector along which I want the integration is r vector and vector field capital F, then capital F dot dr vector integration from A to B, where A to B are point on the line. This is called line integral. Consider this is the line. There is point A and there is point B, and this is the vector field. Both are algebraic. Now, if I want this vector field integral along this line, then capital F, that is the vector field dot dr vector from point A to B, where A and B are point along the r vector. This is called line integral. This is called line integral. Okay. Now consider this vector field is a force field. Then force field dot dr vector is nothing but the work done by the force along the r vector. If force and r vector are along the same direction, then work done is maximum. If force and r vector are orthogonal to each other, then dot product would lead it to zero, no work done. Otherwise, as per the angle between force vector and r vector, work done is proportional to that, inversely proportional to that. If angle is 0, maximum work done is there. If angle is 90, zero work done is there. So if vector field is capital F, that is force field, then force field dot dr vector is the work done. Now we went on the discussion that what is path independence. Path independence means if I am calculating the line integration or work done, if vector field is force, if I am calculating line integration of vector field capital F along any vector dr vector, line integration capital F along any vector dr vector, then this line integration or work done is only dependent upon the vector field capital F, not on the line vector, only capital F. And since I want work done from point A to B, then A and B. If I see the work done or line integral, there are four entities. Integration from A to B, two entities. Vector field capital F, third entity. dot dr vector. R vector is the fourth entity. If I calculate this, so if I calculate this integration, first I have to calculate the integration, that is vector field capital F dot dr vector. Whatever the integration comes, that will be a algebraic function. That is also called potential function. If this, then in the algebraic function, I have to set limit a to b. A to b. That is, if the net result is algebraic function, that is small f, that is the net result of capital F dot dr vector, that is small f, that is pure algebraic function, then fb, function at point b minus function at point a, fb minus fa. The if integration is from a to b and net integration inside it is small f potential function, then we have to set the limit. So fb minus fa, small f, that is the integration. It is path independent. Now in output we have three components, that is function small f, b and a. If small f is only dependent upon vector field, not on the r vector, because if I did integration with r vector, if I keep changing r vector, earlier we took the vector as, if I take a vector as a straight line, point a and point b on the vector, then r vector is a straight line, but not required. Point A and point B will be are fixed point, but this line can be circular. A and B are fixed, but this line can be circular. In that case, R vector is again vector field. So, if this is a circular, parabolic, whatever, the net FB minus FA, end result what we are seeing, FB minus FA, is same for whatever R vector I am taking, straight line, circular line, parabolic line. In that way, we say that the net result what we are getting, it is independent of what line we are taking for the line integration. It only depends upon capital F, that is vector field, and point A and point B, because irrespective of R vector, the net result is small f, a small fb minus fa is same. Then it is called path independent. If it is path independent, means it is dependent upon vector field capital F at point A and point B. If I do A and B integration plus B and A integration, then it is same as A to A. Since it is A to A, it should be 0. But if it is not path independent, then there is a high chance that for certain path, if I calculate capital F dot dr from A to B, and then I calculate from B to A capital F dr, both will not negate each other. If they don't negate each other, then A to A, if I say, it won't be 0. That is curling. There we introduce terminology called curling when it is not path independent. If it is not path independent, then the work done or line integral from A to A, that is A to some point to some point, and some point back to A, that is closed loop. So A to A means not same point I am saying. A to A means if it travels and then come back to A, then the line integration should be 0 for all possible paths, that is from A to come back to A. It can be a straight line, it can be circular, it can be parabolic, it can be semicircular and then a straight line, whatever it is. So for the closed loop, for the circular loop, for all possible r vector, if the line integral is 0, certainly then it is path independent. If it is path independent, then A to B, if I take integral, then this integration, what we get, the potential function, this potential function must be dependent only on vector field. If that is the case, then it is path independent and it is not dependent upon the r vector. Now we are seeing curling. So when we are seeing curling, then we have taken x-axis and there is a point called A and there is a point called B on x-axis, and now from A there is a line like this. This is point is C, the top point is C. From C, I take a line like this, C to another point D. From D, I take another line like this, D to B back and B to A. Okay, this is another path, that is from A back to A. This is rectangular path. This is R vector. So if I am calculating the line integral, consider the force vector, consider the vector field. This is repeatedly I am saying, consider the vector field as x plus yi plus 0j, x plus yi. If that is the case, then force vector is along this direction. What is the work done, or what is the line integral? So if then the force vector along this R piecewise, piecewise I am calculating, because integration I can break into piecewise. I want integration from A to A, then A to C, C to D, D to B, B to A. Now this integration, line integral, will be 0 because force is in this, vector field is in along I direction, 0. This side also 0. Only it will be positive this direction, positive or negative, non-zero this direction, and C to D direction. So in C to D direction there is a line integral, and back B to A direction there is a line integral. Since B to A force is in this direction, it will be negative. It will be negative in the sense that if we recalculate, then it will negative, B to A will be negative, means work done is in this direction, not in this direction. So it's all right. So work done is in this direction here also, and work done it is in this direction here also. Okay, so very well. So force into kind of force into displacement. I mean vector field line integral. If vector field is capital F, then it is work done. Now this line integral is 0 because vector field is perpendicular. This line integral is 0 because vector field is perpendicular. What about this line integral from C to D, where force is, or vector field is x plus y? Consider y is 10. This is what example I gave. Consider y is 10. If that is the case, then x plus 10. Or consider there is no x. There is no x, and it is y plus 1i. Y plus 1i. Then it is 11. 11i. Whereas here y is 0. So it is I. Just I. So it is powerful. So here the vector field is powerful. So if I take the height as 10, then let's go with the earlier equation, x plus yi. If I take x plus yi, then this vector field is x plus 10i. Integration of x plus 10i with the r vector is nothing but I vector. R vector is nothing but I vector along x-axis. So that is now dx. Okay, so r vector is xi. This is what we can say. Any point on the r vector is xi. So it will become, or if I take also xi plus yj, it will be dx. So net integration is x plus 10 dx. X plus 10 dx. Whereas along this axis integration is x plus y. Y is 0. So x dx. X dx. Now this integration x plus 10 dx, x plus 10 dx from point C to D, where C and D, the net amount is same as B to A. So it will result in positive work done, plus integration of 10, integration of x plus 0. So x dx from B to A. A is small, B is more, from B to A. So it will result into negative. It will result into negative. So this is positive work done and this is negative work done. Negative work done because we are doing from B to A. If I calculate A to B, because force is in this direction, then it will be positive, whatever it is. So this is 0. This is 10 plus x, x plus 10 dx. This is 0 and this is x dx, B to A. This is negative, this is positive. Positive is more. So the net line integral in a closed loop is not 0. If it is not 0, that is A to A, This is not path independent. It must be 0 to be path independent. Path independent means it should depend only on begin point, end point and vector field. But it depends. If I calculate from A to B, B to A to B and B to A, that is A to A, the line integral is A to B, then B to A. Then whatever work done is there, this will be like exactly negative. So here A to A is for path that is a straight line, A to A is 0. So line integral is 0, net work done is 0. But I cannot say it is path independent because A to A is 0. But if I take another path, then it is not 0. So it is not path independent. If it is not path independent, it will generate twisting, rotation, because this is line integral 0. Here line integral is powerful 0. Here it is negative in this direction. So net line integral has some value and this is more powerful. So if there is a vector field in this direction, if I place an item here, vector field will try to push it along the vector field. But since one side vector field is more powerful, thick, and this side vector field is thin, so it will try to rotate it like this. It will move it and it will rotate it like this. This is called curling, whatever it is. Now, I know now that if my vector field is not, if my vector field is in I direction, if my vector field is in I direction, but if I move from x-axis, if I move from x-axis towards y, then vector field strength, the power of the vector field is changing. So, if I have a vector field capital F equal to F1i plus F2j, the vector field capital F is equal to F1i plus F2j. If that is the case, then we have x plus yi plus F2j. F2 is 0 here. So, if that is the case, then F1, that is x plus yi, F1 is something else here, the magnitude, direction is here. And F1 here, that is x plus y equal to 10, 11, 12. F1 keep on changing if I change the y. This proves that df1 by dy is not 0. F1 is changing as we go along y. df1 by dy is not 0. It is changing. If df1 by dy is not 0, it will produce curl. It will tend to rotate the item if you place in the vector field or force field, then force will force the item in this direction, but it will keep on rotating. This is curling. Okay. Now how I can say that even if I have df1 by dy is not 0, then still there won't be any curl. It is possible. It is possible if this component, the vertical component is not 0, now I have 0. When it will not be 0? If vector field has j component. Consider vector field has j component, x plus yi plus x plus 2yj or x plus sin yj, x plus yi plus x plus sin yj. If that is the case, then work done here, net work done along any line is x. The line vector generic way to represent any line vector is x comma y, position vector xi plus yj. Then dr vector is dxi plus dyj. If it is a straight line or whatever it is. Okay, now we have now f1i plus f2j, that is capital F vector, dot d of xi plus yj, dxi plus dyj means f1 dx plus f2 dy is the line integral. f1 dx plus f2 dy is the line integral. If I am talking about this line, then there is no x component. Everywhere it is 0 comma something 0 comma, because there is no x component. If that is the case, then this dx factor will go up. Dx factor will go up. If that is the case, dx factor is going out, then I have only f2 dy. F2 dy, or anyway, I have F1 that is along x-axis and F2 along y-axis. So if I am calculating along y-axis, then F1 factor is ruled out because F1 is along x-axis, this is y-axis. So F1 has no effect on this line integral. Only F2 has effect. So F2 dy. F2 dy is the line integral on this side. Now this side we have calculated, that is x plus 10 dx. Now this side again F2 dy. Now if I have x plus yi plus x plus 2yj, then the F2 component is x plus sine y, x plus sine yj, then F2 component of vector field is x plus sine y. So x plus sine y dy is the work done. So consider this vector field is like this, because F1 and F2 consider it is positive. If that is the case, then x plus sine y dy, x plus sine y dy, x plus sine y dy, then it is a positive work done or line integral. This, and then if you come back, then from d to b, where b is small and d is higher, d to b, then this work done will be negative. And this is powerful. Can you see? X plus sine y. If y is increasing, sine y will increase. So this is more powerful. So this proves that if I take the net line integral, then this has some value and this has some value. Now this value and this value if I take, then this has this direction. This direction, this has positive line integral if it is in this direction. And then this is positive line integral, it is in this direction. This is negative line integral when it is in this direction. So it is positive when it is in this direction. Makes sense, right? Because if I am calculating line integral of F2 dy from this point to this point and F2 dy is positive, then d is more and b is less, d to b, then it will come as negative. This proves that the line integral is positive in this direction, negative in this direction. If that is the case, then if we see the line integral along this and this, then this is more powerful. So more line integral in this direction. If I take line integral along this and this is more powerful and it is in this direction. So this direction and this direction, they nullify each other. Then still, then curl can be 0. Even if I have df1 by dy, df1 by dy is not, df1 by dy is not negative, but again we have df2 by dx. As we change the x, then df2 component is changing. Here it is less and here it is powerful. So if I have df2 by dx and if I have df1 by dy, then they nullify each other. If they are together, if they are same, then df2 by dy and df2 by dx and df1 by dy, if they are same, looks like, we are not sure, we know that they oppose each other. If there is df2 by dx component is there and there is another component df1 by dy, they oppose each other. This is what we are saying. If they oppose each other, but once they oppose each other in same fashion, in similar quantity, then net rotation tendency of this vector is 0. It cannot rotate. Okay, earlier it was f1, df1 by dy was there, so it was trying to rotate like this. But once df2 by dx is there and it is trying to rotate like this, it is also trying to rotate like this. They are nullifying each other. If that is the case, then what should be the relationship between df1 by dy and df2 by dx so that curl will be 0? Okay, is it that I have to multiply with some scalar? What it is, that we will see. But we know that if df1 by dy is there, if df1 by dy is not there at all, it's possible. if f1 is only function of x, if f1 like vector field capital F is xi plus yj, xi plus yj minus y minus xi plus minus yj sin xi plus cos yj. If f1 has no component of y, then df1 by dy will be 0. If f2 has no component of x, then df2 by dx will be 0. If I change, f2 is in y direction, j direction. f2 is going along x axis and there is no change is seen in f2. And f1, that is along x axis, it is going along y axis and there is no change is seen in magnitude of f1. Then there is no curl tendency it will produce. If that is the case, then certainly it will be path independent. Can you see it? Then from line integral of capital, when vector field f along dr vector from a to a will be 0. A to a will be 0. Now a to a, you can take a to c, c to d, d to b, b to a, or a to a can be circular path also. This is point A. You take A to A as take complete path, or A to A here, A to some point here and come back like this. Whatever path you take, A to A will always be 0 if there is no df1 by dy and there is no df2 by dx. But if they are there, then what is the relationship they should carry so that f dot dr point A to A will be 0? What relationship df1 by dy and df2 by dx should make so that a to a capital F dot dr vector will be 0? That is the question. Okay. Now we are proceeding something towards it is called Green's theorem. So what Green's theorem is, we will see. Consider this is line independent, path independent. What we have seen in the path independent is, if something in calculus, the normal calculus is integration from a to b. If there is a algebraic function small f, then integration from a to b, gradient of f dot dr vector is nothing but fb minus fa, where every f is small here. So if I integrate a to b, gradient vector of algebraic function small f dot dr vector equal to fb minus fa. This proves that this fb minus fa is dependent upon only three things: f, b and a. If I see here, then I have four things. F, all are small. F, gradient of f dr vector a to b. So net result is not dependent upon r vector. If this is the calculus form, then it is path independent. But we calculated line integral is a to b capital F vector field of dr vector. So if capital F is equal to gradient of f small f, then it is certainly line path independent. If that is the case, if it is path independent, then vector field capital F is gradient vector of potential function of small f. Makes sense, right? If that is the case, then gradient of a small f is df by dxi plus df by dyj, whereas capital F, that is the vector field, is f1i plus f2j, whereas gradient vector of a small f potential function is dfxy by dxi plus dfxy by dyj. This proves that dfxy small f, dfxy by dx equal to f1 capital F, dfxy by dy small f equal to f2 capital F. If that is the case, then can we see dfxy by dx? If I say fxy, it is small f. If I say f1, f2, it is capital F. So dfxy by dx equal to f1, dfxy by dy equal to f2. Now dfxy by dx, now let's differentiate with y also. So dfxy by dx dy, dx dy is nothing but differentiating along xy plane, that is dx dy. If I, this is Cartesian coordinate, if I try to do differentiation along xy plane in polar coordinate, then it will become dfr theta by r d theta dr. But now it is in Cartesian, so dfx by dx. Now I am differentiating with y also. So dfxy by dx dy equal to, earlier it was f1, now it becomes df1 by dy. dfxy by dx dy equal to df1 by dy. dfxy by dy was there, dfxy by dy dx. Now I am differentiating with x also. dfxy by dy dx. Top is dfxy by dx dy. Here dfxy by dy dx equal to df2 by df2 by dx. dfxy by dx equal to capital F1. dfxy by dy equal to capital F2, where fxy is potential function, small f. Now, first one I am again differentiating with y. Second one I am again differentiating with x. So, first become dfxy by dx dy equal to df1 by dy. Next one is dfxy by dy dx equal to df2 by dx. Both are same, right? dfxy by dx dy or dfxy by dy dx. dy dx is also xy plane and dx dy is also xy plane. They are same. If they are same, then this is also same. So df1 by dy is same as df2 by dx if it is path independent. If it is path independent, the line integral in a closed loop line, that is a to a, in a circular loop, a to a, or I can say in a circular loop, capital F, that is vector field dot dr is 0, dr vector is 0 if it is path independent. But also I know now, if it is path independent, then capital F is, if net integration is small f, then capital F is gradient of a small f. This is what I know. Now you know more thing. If that is the case, then df1 by dy equal to df2 by dx, because dfxy by dx dy is same as dfxy by dy dx. If that is the case and it is path independent, then df1 by dy is same as df2 by dx. Means if I had taken a rectangular path and if df, then indeed it is, if df1 by dy equal to df2 by dx, if f1 is changing, consider this distance is very high. The distance I had taken for f1 to change, this is very high. If df1 by df1 by dy is there, then difference between this line integral and this line integral is very high, because I have taken so far. But here I have taken so small. So difference between df2 by dx and df2 by dx, then it is very small. Here it is very high. Then how curl will be 0? It will be 0 because you have taken this line integral is very high. Okay, here df1 by dy is very high. So in that case, the line integral where f1 is concerned, so that f1 difference is very high. But net line integral, if you take, since you have taken far distance, the r vector, the point 1 to point v, another part, there are two parts of integration, right? That is vector field f and r vector. Then limit a to b. So a to b, that limit is very high in this section. So integration is, line integral has some value. Since it is very high, even though df2 by dx is not that much, but still since integration level is high, the difference will be very high. Like I am saying df1 by dx, I am taking long distance. In that way, since df1 by dx has some value and dx is high, then f1 difference will be high. So it will nullify each other. At the end, the result is same. So you take real rectangle where height is very high, width is very small and height is very high, then this line integral difference will be very high. Okay, or if you take very high, and here the force difference, the vector field difference will be very small. So vector field difference will be very high. So net line integral will be full, will be 0 only. So it will not produce any curve. It will not produce any curve, whatever it is. Now we have learned that if it is path independent, then df1 by dy and df2 by dx are 0. But do you see one thing? If line integration for a curve is capital F dot dr, then what is df1 by dy and df2 by dx? There is one Mr. Green comes into the picture. Now, Mr. Green is saying that if in a closed loop, if line integral is 0, if it is path independent, and it is df1 by df1 by dy and df2 by dx are the same, if it is path independent. If it is same, df1 by dy and df2 by dx are same, this proves that df1 by df2 by dx minus df1 by dy is 0 if it is path independent. df2 by dx, where they are same, minus df1 by dy equal to 0. Okay, then can we calculate line integral with this? What is this if it is not 0? If I had taken a rectangle, and df1 by dy and df2 by dx, if they are not same, then it will produce a curve. It will produce a curve. This is called curl factor curve vector. How much curve it will produce? That is df2 by dx minus df1 by dy. If both are same, then it will not produce the curve. But if they are not same, then how much curve it will produce? That tendency is determined by df2 by dx minus df1 by dy. Okay, but anyway, now Green is saying that if I am trying to calculate line integral in a closed loop, and if it is path independent, then from a to a, or in a closed loop, then capital F dot dr vector is 0. If it is not 0, then it is not line independent, then it is not path independent, and it will produce curl. What is the net curl it will produce? That is df2 by dx minus df1 by dy. True. Now consider this is a rectangle, point A and point B, A to C, C to D, D to B, B to A. There is a rectangle. Now Green is saying still you can calculate the line integral in a closed loop. If this is a closed loop, and if I go counterclockwise, from here I start, I go to B, B to D, D to C, C to A back. It is a counterclockwise, and it is a closed region. If it is a closed region and f1 and f2 are df2 by dx and df1 by dy, they are continuous in this closed region. There is no hole anywhere. They are not anywhere, they are undefined. If that is the case, then the line integral that we can still calculate from the df2 by dx minus df1 by dy. That is whatever comes as df2 by dy minus df1 by df2 by dx minus df1 by dy. If I integrate this with xy plane, that is dx dy, along this surface, dx dy integration means along the xy plane, df2 by dx minus df1 by dy. If this term, that is the curl tendency, if I integrate along the xy plane, that is dx dy, and that is the surface, along this surface, that is xy plane, that is closed by the surface. Here it is rectangle, A to B, B to D, D to C, C to D, or it can be circle, whatever it is. If it is a closed region and there is a surface, then df2 by dx minus df1 by dy dx dy, if I take in Cartesian, in polar r d theta dr, then it will be df2 by dr minus df1 by d theta, whatever. If I integrate for this closed surface, again it will generate the line integral. If it is path independent, then it is 0. In closed loop, if it is not path independent, then net line integral, that surface calculation will give the net line integral. But df2 by dx minus df1 by dy is the net rotation tendency that is the curve. This is Green's theorem. So integration in a closed loop or a to a capital F dot dr vector is same as integration in a surface bounded by this boundary, where I am calculating the line integral, bounded by that boundary, that surface, df2 by dx minus df1 by dy along the xy plane, dx dy. That is same. This is what Mr. Green is saying. We'll do some workout and then we will proceed. I believe a Stokes theorem and many theorems are there. This is the toughest part in calculus, that is curling. Okay, so we will proceed on.